This is video 3 of our chi-square test, and let's go right to looking at an example. So this is example 2-5, and what are we given? So we're looking at salinity measurements. So we have 48 salinity measurements. And we find the mean is equal to 49.54, and the standard deviation was at 9.27. Okay, and the question being asked is the sampled population normal? Does it have a normal probability density function? And so our null hypothesis is the sampled population has a normal distribution, and the alternative is the sample population does not. Okay, and here we're given alpha, the significance level of 0.05, 5%. Okay, so we have our 48 salinity measurements, and we have to test whether the frequency distribution of those 48 salinity measurements adequately follows a normal distribution to test our population. That's what we have to do. So the first step is to convert xi to normalized values. So we'll convert that to our z statistic. Okay. And then so we're going to divide our range of z's into k bins. And in this case, let's say k is equal to 5. Okay, so let me sketch that test distribution out. So we're testing whether it's normally distributed. Okay, so that's our test PDF. And if we're going to divide it into 5 bins, let's make it somewhat simple on ourselves and divide it in such a way that P is equal to 1/5 for every bin. Okay, so that means that we have to give different values of Z to our bins. I'm going to sketch these so the area within each, under the curve within each bin is approximately equal. So that looks okay, I guess. And we have to look up in a table or use norm INV, the MATLAB function, to determine what values of the z those are, and it turns out that it's minus 0.84, and that's what encompasses 20% of the data to the left, to all the way to minus infinity here. And the next z value is minus 0.26, And it's a symmetric curve, of course, so the next value is positive 0.26 and then positive 0.86. Again, the area under the curve in each of these bins is 0.2. So little pj is equal to 0.2, not 0.5, 0.2. Okay? And so with that set, then the expected number within each bin is also the same. That's equal to pj times the number of measurements in our sample, and that's equal to 9.6. Okay, so if we divide, once we convert our data values to z-values, and look for all the z-values that are less than 0.84 minus 0.84, all the z-values in this range, we get observed numbers in each bin of 10, 11, 10, 5, and 12. That's the number of observed data values in each bin. And so we can, from there we convert our chi-squared statistic. And remember, we're summing over 5 bins of the difference between the observed, I keep writing a Q there, minus the expected value, and that's squared, divided by the standard deviation of each bin, which was the square root of the expected number. And so therefore little EJ is squared, and we get a value of 3.04. So the next thing we have to do is decide on the critical value of chi-squared. And before we do that, we have to decide on the number of degrees of freedom we have. So normally it's nu is k, the number of terms we're adding here, minus 1. Okay, but in addition, we have to subtract 2 more parameters because we've estimated mu and sigma using the corresponding mean and standard deviation of our sample. So we have to subtract 2. These are the number of parameters estimated minus k minus 1, and that's equal to 2. So again, this test is a right-tailed test of chi-squared. So this is chi-squared because we only care about values that are unusually high. We don't really care about values that are low because the low values represent a very good fit to the test population, the test PDF. So the critical value is, well, it's chi-squared, and our significance was 0.05, and we have 2 degrees of freedom. And that's, if we look that up on our table, we get 5.99. And the chi-squared value that we calculated by the sum of our normalized misfits was less than 5.99. So H naught, can it be rejected or can it not be rejected? It cannot be rejected at the 5% level of significance. Okay, so that concludes our 3 video series on the chi-squared test of a known PDF.